Hi, in this video we're going to talk about the energy bucket. Now the energy bucket is a concept which lets you visualize very effectively how much energy you have left to get rid of before you reach your target. So it has kind of a funny name, the energy bucket, but we'll see why we call it a bucket in a little bit. Now, to review a little bit, so we have to worry about the vehicle's energy. And when we talk about the energy, we're talking about the total specific mechanical energy, and we just call that E. E is equal to v squared, which is the velocity squared, divided by 2 times the acceleration of gravity, plus h, and h is just the altitude above the surface of the Earth. So you might recognize this is just the kinetic energy and the potential energy. You can kind of tell, when you're going really fast in outer space, this velocity squared term is going to be enormous, much larger than this altitude term. It's going to have a big altitude, but this energy term is going to completely dominate the velocity term is going to completely dominate the altitude term. So with that in mind, let's consider, in how you lose energy, how you actually fly down and lose your energy. So your energy loss comes from 2 sources. They come from lift and they come from drag. So lift and drag. These 2 forces will bleed off energy out of your system. And you might say, well, why doesn't gravity bleed out energy out of your system? Because if you're going down and gravity's working on you, your altitude is decreasing. But you might know that gravity is a conservative force, which means that you can trade altitude for velocity, or you can trade velocity for altitude. So just when you're under the influence of gravity, it turns out your energy is constant. So this term plus this term is a constant when you're only acting under the influence of gravity. So that's why in outer space, when you're in an orbit and you're not being acted on by an atmosphere or anything else, your energy is actually constant when you're in outer space. But as soon as you start bleeding off energy due to lift and drag and other aerodynamic forces, you start losing energy and you're going to keep on descending further into the atmosphere. So over here I've sketched a picture of just a sample energy bucket. So on this axis is the energy, so as you go up there's going to be more energy up here than there is down here. And then down here, this is the downrange, or delta R, downrange distance. So here we say this point right here is 0. We'll say this is where the target is. Relative to here, this is how you measure how far away from the target you are. So if you're over here, my sign convention is that this is negative downrange. And when you're over here, you have positive downrange. This means if it's negative, you're not flying long enough. And if you're positive, it means you're flying past the target. You're flying too far. So let's take a look at what this crazy looking thing is. So you might notice that there's these 2 lines here, this pink line and this yellow line. The pink line represents the lift up trajectory and the yellow line represents the lift down trajectory. So you might be saying, well, what do you mean by that? So these 2 lines define a bucket. And we define this bucket to be this green area right in here. This is the green area, the bucket. And what this means is, now it says, okay, from where your current position is, let's predict a trajectory if we flew full lift down all the way to the ground. Now what would happen is we would get something that looks kind of like this. So we would fly, and we'd fly all the way down, and we'd fly down very quickly, and we'd land very short of the target. But what we're going to do is we say, well, okay, that is the worst case. That's, that if we had to really stress, that's what we would do. So what we do is we take this trajectory, and then we shift the entire thing over to this yellow line. We take this anchor point, the terminal point, and we move it over to the target so that we shift the entire trajectory by that amount. And then what we get is this curve that looks like this. And this represents a boundary. So if we are past this boundary out here, it means, okay, even if you fly full lift down, you're not going to reach the target. If you're right here and you fly full lift down, you're going to come down right here. You're going to fly past no matter how hard you try. So what this line represents is a boundary. It says, hey, if you want to have any chance of reaching the target, you have to stay to the left of this boundary. Now, if that concept makes sense, now this next one's going to make a lot of sense too. This represents the lift up trajectory. So if we imagine from our vehicle's state right now where we currently are before we've flown in, we predict where we will go if we fly a full lift up trajectory, or a bank angle of 0 degrees. So it'll look something like this. We're going to fly down and then do a little bounce and then come back in. And we're going to land well past of the entry. And so what this means is, well, let's anchor, or let's set this final point where the target is located, and then let's shift the entire trajectory over there. So what we get instead is we get this boundary over here where this says, hey, if you are over here, this means you don't have enough energy to be able to reach the target. For sure, you are guaranteed to land short. So this is like a boundary saying you have to have more energy than this line. So more energy than this line. So what this means is you need to stay in this green area. This green area is the safe zone, and we call this the bucket. Stay in the energy bucket. And so hopefully you can get a brief idea of what this means. These two lines represent boundaries, and you need to stay in between these two boundaries. If you fall outside of these boundaries, it means that you don't have enough energy to fly long enough to stretch out your trajectory to be able to reach the target, or else you're going to have too much energy if you're over here, and you're going to fly past the target. So that's kind of a brief overview of the energy bucket. But let's think about some of these curves that we were looking at up there. So I'll draw another energy bucket just so you can see what I'm talking about. So if here's 0 downrange, here's the downrange axis. And here is the energy axis. And let's draw our trajectory like this. So if, say, our vehicle is right here, let's say here, this is our trajectory, that we do something that looks like this. Oh, okay, so what is this? Actually, that's not a very good one. Let me draw a better one. So it'll look something like that. So what does this mean? It means as we fly along, we are bleeding off our energy. So up here the line is pretty flat. It's not really going down very much with respect to the energy axis. So what this means is we're really not in the atmosphere, because you lose energy due to lift and drag. So lift and drag. That means we must be really high in the atmosphere and not feeling very much aerodynamic forces. But as this line starts descending downwards, it means, hey, we're losing energy with respect to our target. So it means that we are entering the atmosphere and we're starting to lose energy because of lift and drag. So as we start flying down here, we keep on losing more and more and more and more. But what do you know? We've actually flown past the target. We had too much lift, is what this means, that we flew past the target. So what we do instead is we say, well, okay, if we have too much lift, let's decrease our lift. So let's fly with a trajectory with less lift. So then it starts looking like this. We say, okay, now we decreased it too much. So it's kind of like the Goldilocks problem. You have to kind of figure out how much lift you should give to be able to hit the target. And there we go. We hit the target by making sure we bleed off energy at an appropriate pace to make sure we have 0 energy by the time we reach the target. So what does this really mean? You can kind of think of this, so imagine in a physical context, if here's the target, and let's assume that the Earth is just flat. That'll make the drawings easier for me, because I'm not a very good drawer. There we go. So here's the Earth, and let's say here is the spacecraft. And then let's say here is the top of the atmosphere. And down here, the atmosphere is really thick. Much, much thicker down here. So this is altitude on this axis, and we'll show that by h. So as you can see, from where we are right now, we're a long ways away from the target. So we have a pretty big downrange distance to the target. But as we keep flying along, because this is how our vehicle is flying, and let me take that back, we're not flying like that. Our vehicle flies at an angle into the atmosphere. We call this angle, here's a line, so we call this angle gamma. This is the flight path angle. And so we fly into the atmosphere, and so when we're very up high in the atmosphere, we're not going to bleed off much energy, but we're still flying towards our target. But as we get deeper and deeper into the atmosphere, we're going to have more and more accelerations and lift and drag on us because we're seeing a denser atmosphere. So then it makes us slow down. When we slow down, we lose energy. And when we lose energy, then we start falling more. So eventually we keep falling into the atmosphere. And we're losing energy to lift and drag, but we're kind of falling towards the target. So if we lift enough, we can stretch out our trajectory to fly extra long, kind of like a glider, and we might fly past. But if we don't use enough lift, then we're going to fall short. So we have to figure out what's just the right amount of lift to fly so that we can reach the target. So it sounds kind of like a simple problem, how do we pick enough lift to fly? Well, it's actually a complex question, and that is what entry guidance is all about. Entry guidance is trying to answer how much lift should you provide so that you can reach the target, even when bad things might happen in the future. Bad things that you can't predict, like you are flying into a really windy day, or the atmosphere is really bad and it doesn't give you as much lift as you think you should have, and other things like that. That is the problem of entry guidance. Guidance is responsible for getting you safely to your target as quickly as as safely as you can.